Okay, today we're talking about parabolic motion again, and this is the beginning of a great equation. We use meters for this class, and so you've got the beginning because we're on Earth, and then you should be able to do these next couple parts if you know what's going on. As the guy is tossing the bottle up in the air, he throws it at a rate of, let's say, 5 meters per second. And the levee is up. Of course, this is the Chevy that's by the levee right here. He is up a total, when he starts throwing it, this distance all the way up to here, it is going to be 50 meters. All right, so we got a starting height. We got a velocity. You should be able to write me an equation for that. Type it into your calculator. Figure out what's the highest the bottle ever went. Of course, I'm asking for the vertex, but the calculator doesn't know that. The calculator thinks you're asking for what? Maximum. Very good. All right. I want to pair you up with somebody so you can ask them when you get stuck. I'm going to pause for a second while I do that. Okay, I got my groups assigned, so I want you to try to find that maximum, and would you please compare it with the other person when you are done? See if you've got the same maximum. If not, then go through the process together so you can tell where the mistake is being made. Remember, you want to go to the left side of it, and then you want to go to the right side of it, and then you want to go right on top of it for your 3 steps. See what I'm going to do. Okay, pertinent question was asked, what is the equation anyway, just to make sure that you typed it in right. What did I say, 5 meters per second? So that's a 5x. And then the last was starting height, 50. The bottle was 50 meters up off of the bottom of the levee. All right, got an answer or question? All right, I will do that for you. Hold on just a second. Okay, so here we go. You're supposed to find the second, calculate the maximum. Let me show you that on the calculator. Okay, so when I hit graph on this equation, mine looks just ridiculously small. So just a reminder, if I needed to, I can zoom box. Zoom box means box in the area that you wanted to zoom in on. So I'm going to get down closer before I start my zoom box. Get the little plus sign like right about there. I'm going to hit enter, and then I'm going to go out and go far enough to the right, and then I just keep going down until I have the box that I want. There, that looks good. If I could zoom in on that. Now it redraws the graph, zoomed in to just the place that I wanted. Cool. Okay. So now, what was it? Well, how about I just do it for you. Second, calculate the maximum. It's number 4. And remember this left bound, you want to get to the left of the top, hit enter. Then you go to the right of the top and you hit enter. And then guess, that means get right on the top and hit enter. And the final answer was 0.51 gives you 51. Ooh, that's a dyslexic kind of challenge. 0.51 comma 51. All right, so what does that mean? That means time was half a second. Height, 51 meters. So what's the highest that the bottle ever went? 51.27 to be exact. 51.27 meters. And what was the time at which it reached that height? 0.51 seconds, or about a half a second after a guy threw it, it reached its maximum height. Raise your hand if you got the same thing as I did. Okay, good. Now I want you to see if you could handle a couple more little things that they could ask you. They could say, when was the bottle at 50.5 feet? 50.5 feet. Now that's not giving you a time. Don't go second calculate value. That'd be if I gave you a time. I didn't. I gave you a height. So watch. Go to the y equals. Type in there a line that's going to go straight across at 50.5. that does is if I hit graph, it'll put in a second line here. And the question is when it goes over that line. So then we need to find that spot where they touch. That's second, calculate the intersect. Second, calculate the intersect. Number 5. And then my advice on this is just get really close to the intercept you want, which I want this further one to the right. So I get really close to that, and then I go enter, enter, enter. I know it's kind of gaming the system, but it's a lot simpler than trying to figure out what each of those questions is. Okay. Intersection 0.9 and 50.5. What the heck does that mean? It's got a height of 50.5. That's what I wanted. What's that 0.9 then? Yes. 0.9 seconds. Yes. So in other words, just a little less than 1 second, the thing was at 50.5 feet. If you understood that, would you please find the other place where it hit 50.5 feet? That's going to be on the way up. Got it ready? Hold that thought a second. You having trouble? Or I'm going to pause for a second. Go. All right, so I had to check with a few people to make sure they were doing this right. And hopefully, watch me do it once. Steve, you did it the same way. Listen, 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 listen. All right, so I go to second, calculate the intersect, and I go right near where they touch. And I go enter, enter, enter. Did you get 0.11 seconds? Raise your hand if you did. 0.11. Okay, good. Now, let's change this question one more time to a different thing we could ask you. Where is the bottle at time 3 seconds? Everybody go through the process you do. See where is the bottle at time 3 seconds. Miss BH, what did you get? Can anybody verify 20.9? All right, I'll show you the process for those of you following along at home. Second, calculate the value, that top one, and then X brings up X equals Blinky. X is time, remember that? Try to keep track of what we're doing here. Time is 3. Enter, and it brings me to the spot, 20.9. So that means it's 20.9 meters off the bottom of the levee, I guess we were doing. Chevy side of levee. All right, let's do one more, except I'm going to give you just a whole bunch of details, and you have to get right to the answer that I need. Okay? So this one is a problem about Hawaii. When I went to visit Hawaii, I got a chance to hear how they would celebrate the king's birthday, or when they'd have special people come and visit. They wanted to do like fireworks. Well, in Hawaii, they hadn't invented fireworks like they did in China, and so they used something else that was really cool. Hawaiian tradition would be they would go up on this big peak by the ocean, and here's the ocean, and they would start a fire way up here, and then they would get some great big logs going in the fire, and once they are all like burned pretty thoroughly, so there's lots of ash on them and stuff, lots of coals in the logs, they would take these big logs and toss them off of the top. So I'm going to do my best impression of a log that's on fire. And they would toss the burning log off the top and let it tumble down the side. And, oh, the fire's falling, but not the log. Hold on a second here. And it would tumble down the side, and it would land in the ocean. But along the way, it would release so many sparks and stuff that it was sort of like fireworks. Apparently, it was really cool to see in the night in Hawaii. So, the point is, if we took the center of gravity of this log, it does follow a parabola. Okay, because it's basically just like tossing a rock up in the air. It just happens to be a log. The center of gravity of this thing is going to basically follow a parabola. And it's going to be a pretty flat one because you're not going to be able to launch it up in the air very far. It's pretty much going to be more like dropping it off the side. But that's still a parabola. Okay, so if I grab this, I move it down. Okay, so let's say it's more like that. That's still part of a parabola. My question would be, given these facts, they are 300 meters up when they start this launch, and they toss it. Think about this. It's a heavy, big, heavy log. You can be able to toss it very fast. How many meters do you think you could throw a log in a second? Meters per second. Okay, 1 meter per second. Then tell me, where is the log after 3 seconds? Pause for a second. We'll figure that out. Okay, so you should have said y equals negative 4.9x squared plus 1x. I could have just said x plus 300 meters, which is a long ways up above the ocean, but I can do some pretty big mountains by Hawaii, so I can believe that. Then I don't need any second line across here, do I? If I did, it would have been asking you something like, when did the log hit 200 meters in height? As in, it's gone down a fair ways, and it's like right here. You know, it's part way down. All right, but what I did ask you was, first of all, I'm going to graph it. Ooh, my axis looks off a little bit, so I better do a window. Let me talk you through how you can figure out what a good window is. X is time. Do we need negative time? No. So we could say just negative like 3 or something. Why am I even using negative anything? Because then I can see the axis. All right, X max, that's the max number of seconds that I think this is going to be in the air. 10 seconds seems reasonable to me. Probably the longest it would be in the air. And then scale, always count by ones. Y min, do I need a negative height ever? No. So I can again use something like negative 3 just so I can see the axis. If I put 0, it's going to mean that the bottom is going to be right at the bottom of the graph. It's hard to see. Y max is the highest that it's ever going to be. 74 meters, not close to enough. I start at 300, so I'm going to go like 350 in case they throw it up a ways. Now, granted, they weren't throwing it up very far because it's so heavy. All right, that's how you'd pick a good chart. Now I've got it graphed looking like this. Now I wanted you to find me where it would be after 3 seconds. Second, calculate value at 3, enter. And did you have 258.9? Raise your hand if you did. All right, good. Now let's do the last 2 kinds of things I would ask you. One is, at what time did the log get to 100 feet off of the ocean? It was, meters. 100 meters off the ocean. At what time was it 100 meters off of the ocean? As soon as I say time is 100, I gotta go to y, because x 100 would be 100 seconds, which isn't going to make any sense in the context of the question. So I got to go to y is, and I put in an equation for that. Y is 100. And then I take a look at where the graph is, and I see, oh, I wish I knew where those 2 lines intersected, because that's when it's at 100 feet. Second, calculate the intersect, which is 5, and then I just get close to them. Really what it's asking, I'll just show you on this in case you're the brainy types want to know this. The 3 enters you do, the first one says first curve, and what it's asking is put the blinky thing on the first curve. One of your 2, doesn't matter which. I hit enter. Then it says second curve, question mark. It's like, am I on the other one that you want to see intersecting? And you say enter. And then the guess, that means you move it over to right where you think they cross. And I think they cross right about there, so I hit enter, and it verifies I was only off a tiny bit. X equals 6.49, y equals 100, and I already knew the y equals 100 part, because I knew it was supposed to be height of 100. My answer is at 6.49 seconds. Raise your hand if you had that one right. Okay, last thing I haven't asked yet. Who knows what it is? What type of question I haven't done yet? Yes, sir. We did do that on a different problem. I mean, ever. Today. What kind did I never ask you yet? Yes? the zeros, which would be what question, though? About, in the context of this log going in the ocean, what is the zero? Where did it hit the ground? No. When did it hit the ground, or what time did it hit the ground? Good. Try that one. Hopefully you know how to find the zero, because the x-intercept is not something they list. They don't list solutions. They don't list roots. But they do list zeros. Just a second. Zero. Oh, yep. Zeros. And then I get to the left of the spot that I care about. By the way, just to be clear, that's the spot I care about. That's when it goes to zero or hits the ground. So I got to get to the left of that, enter. Get to the right of that, doesn't matter how far, I just get far enough and hit enter. And right where I think they touch, which is pretty much right there, and hit enter. And did you get 7.92 seconds? All right. So this firework display only lasts for like 8 seconds. So they probably have a lot of logs. Probably throw them one at a time, and you get like 8 seconds. Throw another one, 8 seconds. So, all right. I think you got the idea in the context of a real Hawaiian problem. Makes me feel warmer on a day like today. All right. So your homework for today is to finish the worksheet that we gave you yesterday. Tomorrow, you're going to have a new worksheet. Yesterday's worksheet, you only are supposed to do 1 through 5. So if you finished it already, goody for you, but most people probably only did 1 through 5. And that's called day 2, I think. I could show you in Schoology here. It's under Applied Quadratics Day 2, and it's that worksheet right there, Applied Quadratics Worksheet 2. And again, we had already done 1 through 5 on this. So you're going to pick up at number 6. Joe Mauer hits a pop fly straight up. All right. Any questions? So just finish that worksheet. That's your homework for today. Tomorrow I give you a different review worksheet. That's under the next official lesson. Back here. Right there, lesson 3, Applied Quadratics Review. And it'll be this one tomorrow. Applied Quadratics Review worksheet. And then the test is on Wednesday. Make sure you have a graphing calculator. I do usually have ones you can borrow, but I can't promise that if you don't get here early. So try to bring your own. Okay, that's all I have for you.